All right, so the next step here in studying oxidation reduction reactions is actually balancing redox reactions. So as I mentioned before, when we balance redox reactions, we're not only taking into account the atoms and how they rearrange and making sure that the number of atoms of a certain element are equal on the left side as they are on the right side of the equation, but what we have to take into account as well here is the electrons. That's what distinguishes a redox reaction. So when we balance, yes, we have to balance with respect to atoms, but we also have to balance with respect to electrons, and that's where the tricky part comes. Okay, so in your notes, follow along. Balancing redox reactions slightly more complex, okay, as I mentioned. We're going to be using something called the half reaction method, okay? So what we're going to do is we're going to basically, we know that a redox reaction is made up of a reduction part and an oxidation part. So what we're going to do is we're going to actually split the reduction and the oxidation parts up. We're going to balance the reduction half separately from the oxidation half. Then at the end, we're going to combine them. Okay? So that's generally what we're going to be doing. We're going to be studying balancing equations in acidic conditions only. So there is another method, which is not beyond you guys. It's just for the sake of time, we're going to focus on acidic conditions. And what that means is that when we need to balance electrons, or, and you'll see if we need to balance oxygens or hydrogens, this is what we're going to do. We are going to be including in our equation water molecules, hydrogen ions, because it's acidic, so there will be some hydrogen ions. We're not going to worry about hydronium ions, okay? We're just going to do hydrogen ions for now. And electrons when we need to balance electrons. So this is super important, and it'll make a lot more sense once we get into it. But if we need to balance oxygen from one side of the reaction to the other, we're going to add water. We cannot just add oxygen, because in an acidic solution, we have water molecules available. In an acidic solution, we have hydrogen ions available. And of course, the electrons, there's billions of them floating around, so we can add those into our mix. Okay, so these steps, again, once we kind of go through an example, these steps will become more real to you. But just here's the real quick outline of what we're going to do. We're going to balance all the elements in the equation other than O and H first. So if we have a lithium ion and then we have a lithium oxide, that's Li, and then there's an Li2O, we have to balance the atoms first. So other than O and H, so we have to balance everything else first, just like normal. Step 2, balance oxygen atoms by adding the appropriate number of water molecules. So here we go. This is where it starts to get a little bit different. If I have 2 oxygens on one side and 1 oxygen on the other side, I add a water to balance the oxygens. Okay? Can't just add an O, but we do have water molecules available in the solution, so that's what you do. Step 3, balance the hydrogen atoms, okay, including those added in step 2 to balance with the oxygen. So obviously we've added hydrogen in step 2, right? As well as adding O with water molecules. So we need to balance all the hydrogen atoms by adding H plus ions in this acidic solution. Okay, so there we go. We've got water molecules to balance the O's, H plus ions to balance the hydrogens. Number 4, we add up all the charges on each side. So charges meaning we've got H pluses, so that's a +1 charge for each one of those. If we have another negative ion for some reason, we add up that as well. And we add up the charges on each side, and we have to make the charges on the left side and the right side equal. And if there's an imbalance, we then add electrons to the more positive side to balance them off. Okay? So we add up the charges and make the charges equal by adding an appropriate number of electrons. And this is just a rule of thumb, I guess, that you might notice here a bit later, but electrons and hydrogen plus ions are almost always on the same sides. So again, once we actually get some practice doing this, this will make a lot more sense, because you have to practice this, and these rules don't mean much to you right now. But we may as well just go over them so that you have some idea of what you're doing. All right. So the electrons on each side now must be made equal. If they are not equal, they must be multiplied by an appropriate integer, that is the lowest common multiple, to be made the same. Okay? So, okay, and what this means here, okay, the electrons on each side must be equal. That's when you're comparing the reduction half and the oxidation half. All right? So again, this will make more sense once we do examples. The half equations are then added together. Okay, so the electrons must be the same between the two equations when you compare the two. They are then added together, and the electrons will then cancel out. So you cancel out the electrons then because they have the same number on opposite sides, and then you form your one balanced equation. Any common terms will also be canceled out. So these steps you'll have to refer back to when you are doing your practice, but then they'll become second nature. And then, of course, you do a final check to make sure everything is balanced. I did put a little note in here about balancing in basic solutions. We're not going to worry about that right now. You're not going to have to do that. But in basic solutions, we can't have any H pluses floating around at the end, right? So what we have to do is we have to add OH minuses as well and balance those off to make more water molecules. So that's just an extra step for basic, which we're not going to do. Okay, so let's balance one, and the one I have in your notes is maybe a little bit more complicated than I want to start with. So I am going to, we're just going to add one here. Let's do one from the textbook, and I'm on page 641, 24A. So I think it would be appropriate for us to do this example together. So we have copper combining with silver nitrate to form copper nitrate, that's copper 2 nitrate, and silver solid. Okay, so let's assign some numbers here. Copper is 0. That's all by itself. And over here, what is copper? It is, well, NO3 we know is a -1 charged ion. There's 2 of them that balance off with copper. So that's to be, well, that's to be +2. Yeah, because 2 plus and 2 1 minuses. Right? All right, so we see that copper is changing, oxidation state. And is it being oxidized or reduced? It's losing electrons, so, right, Leo, lose electrons, oxidized. So, we're going to do this here, the oxidation half, this is sort of what I do. The oxidation half is going to involve copper, and leave some space, write an arrow, and then write your Cu2 plus over here. Now we can just do the ion. This is a soluble compound, so just do the species itself that's being oxidized. Okay, so you can drop because look at this is aqueous. Remember what that means? It actually means that they're ions in solutions dissolved. It's not a solid. So really we have copper ions floating around and nitrate ions floating around. So you do not have to involve the nitrate in this. Okay, so it's just copper solid to copper ion. Okay. Now, yes, we're going to do the oxidation half, but let's just set up the reduction half, okay? The red half over here. Now, which one is going to be reduced, do you think, just by looking over here? Is there a change in charge on either nitrogen or silver or oxygen? Yes, Ag. +1 here, and 0. Very good. So Ag +1, make a little arrow, and Ag solid. All right. So that's how I'm encouraging you to set this up, just kind of like this. Now you can do half a page one, half page the other. That's great. Again, drop the nitrates. This is aqueous anyway, so there's no, this is just ions in solution. They're actually separate anyways. So just focus on the species that are being reduced and oxidized. Okay. So we go back to our rules here. What's rule number 1? Balance all elements other than O and H. Okay. So in our half reactions, copper, is this balanced? 1 copper, 1 copper. Yep. Ag, there's 1 there and there's 1 there. So we're good. You might run into a problem if this was Ag2, right? If this was a diatomic, then you'd have to do this. It's not the case, but if it was hydrogen or something, it would be, right? Or bromine or something, it would be. So that's balanced. Good. What's the next step? Balance the oxygens, if there are any, by adding water molecules. So do we have any oxygens in these half reactions? No, we don't. So don't even worry about it. Okay? 3, balance hydrogen atoms by adding H+. Well, we don't have any hydrogen atoms either, right? This is a pretty simple, straightforward. So we don't have to worry about 2 and 3 right now. Let's go to 4. Add charges on both sides, make them equal by adding electrons to the more positive side. Okay. So, you see how in the oxidation half, this is a 2 plus. On this side it's 2 plus, this side it's 0. So how do I get them both to be 0? Yes, that's correct. You have to add 2 electrons over to this side. Alright, so that those are now, both sides are equal. And where do we add the electrons over on this reduction half? And how many? 1 electron. Okay? You guys with me so far? Making sense? Okay. Alright, so that's number 4. Number 5. Okay, so this is where we're talking about both halves. The electrons need to be made equal. So we've kind of run through all of the, the first 4 steps, and each of these are balanced now. So the oxidation half is balanced according to atoms. It's balanced according to charges. Okay, so charges are balanced, and atoms are balanced over here as well. What step 5 says is that the electrons, okay, have to be the same for both halves. So here we have 2 electrons, and here we have 1 electron. So what we need to do is to multiply everything by 2 over here on this equation to make sure that the electrons are equal. And what I'm going to do is I'm going to actually now, I'm going to just bring this reduction half underneath the other one so that you can see what's going on here, okay? So give me a second. Okay, so I've just brought this down here, the reduction half, I've just kind of brought it down over here. Here's our arrows, right? The electrons are now balanced on both sides of the equation. Do you see how when we look at combining these two now, our electrons are balanced? So all of this work, and again, this is a pretty simple one, we didn't have to add waters or hydrogen, but the whole goal is to get the electrons to balance as well in this reaction. So what we're going to do is we're going to now add these two together. Everything that's on the reactant side, what do we have? We have Cu, we have 2Ag+. The electrons cancel each other out. They're the exact same on both sides, so we don't have to write them. We have an arrow, and we have 2Ag plus Cu2+. Now I know what you're saying, what's happening to the nitrates and all that sort of stuff. Well, remember, these are just ions in solution, so really they're just spectator ions. This right here is the net ionic equation. Okay, it's the net equation. So any ions that are floating around on both sides are not included in this. Okay, so this is your final answer for your net redox reaction. So I'm just going to put that, the net redox. That's it. Okay, so that's the first one. Pretty simple, pretty straightforward. I'll do another example here where it's not as complicated. Actually, I might have to wait till tomorrow to do that, next lesson. But that's your example. I'm going to get you guys to do the next one here, though. You guys can do 24.